Welcome to another warm-up. You know the drill. Pause that video, give them a try. Alright, hopefully you paused the video and that was enough time. Let's see if we can make some sense of these. E to the x minus 2x, where is it increasing? So you could graph it and try to look, but if we want an exact, precise answer, we should definitely take a derivative, in which case we get y prime is equal to e to the x minus 2. I want to know where that's positive and where that's negative, which means I should set that equal to 0. Which means I need to know where does 2 equal e to the x. I hope you know how to solve this, but this might be a reminder moment. I have an x in an exponent. How do I get it down? The answer is almost always take a log. So I'm going to take the natural log because it works out really well with e to the x. I'm going to mainly take natural logs in general. Natural log of 2. If I do the same thing to the other side, natural log of e to the x. You definitely need to know this. Natural log of e to the x, those are inverses. So those undo each other. Thought of it differently, my exponent rule says my x can come out front, and then I have natural log of e would be a 1. In any case, this is just going to be x. All right. Might be a refresher, but you need to know that. In other words, x is equal to negative 2. So here's my little number line here. Sorry, natural log of 2. There we go. That would have been hard to figure out from a graph, that natural log of 2 is this magic place. If I were to take a number smaller than natural log of 2, say 0, I would get e to the 0 is 1 minus 2 is negative 1. So this is definitely going to be a negative over here. It's a 0 at natural log of 2. And again, I'm plugging into my derivative because I want to know where's my derivative positive. And the answer is not below 0, maybe above 0. Let's pick a number bigger than 2. How about 100? How about e to the 100 minus 2 is definitely positive. So that's enough for me to just kind of ballpark. It's positive over here. Because that derivative is continuous, we know that it's not going to skip over 0 anywhere. Right? Our intermediate value theorem actually tells us that. So we really only need to find where is it 0, and then decide at any point where it's not 0, is it above or below? And it'll stay negative or positive. So what did we just find out? We found out that the derivative is positive when it's bigger than natural log of 2. So that means it's also increasing when x is greater, or strictly greater than natural log of 2. Very cool. Not so bad. All right. Where is it concave up? I think I need a bit more room for this. Not too much more. For concavity, what do you need to do? Well, this is a test of my second derivative, so I'm going to need a y double prime, which means I need the derivative of e to the x minus 2, which is just e to the x minus 0. So just e to the x. All right, concave up. That means my second derivative is positive. Where is e to the x positive? Where is e to the x 0? The answer is e to the x is never 0. And it's always positive. Right? If you graph e to the x, it is always above that x-axis, which means that this is always greater than 0, and this is concave up everywhere, right? So it's always concave up. Yep, or you could even write something like for all x, if you want, y double prime is greater than 0. But if the question is asking about concavity, you should really answer it in terms of concavity. So it's always concave up. All right, last one, using a picture to talk about inflection points. So let's just think about the second derivative and concavity again. It looks like it's curving up here, right? This is where it would be above its tangent line. This is where it kind of be below its tangent line. This is where it'd be above. It's curving up again, and then it's kind of curving back down, kind of roughly sketching those curvatures. You don't need to, but it's kind of helpful. And then when am I changing from up to down? Well, it looks like right about here, maybe right about here, and right about here. This last one is interesting. Ooh. My graph got a little funky there. This last one is interesting because it sure looks like that tangent line there might not exist. So it might even be that I don't have a derivative there because of a vertical tangent line. That's the right way to say it, a vertical tangent line. It would still be an inflection point because the concavity is changing from positive to negative, from up to down. Okay, so those are all my inflection points. You can go ahead and write the coordinates for those points too as well, but I think I'm just going to leave it right there just by highlighting those three in green. I hope that was helpful and a refresher. Lots of new stuff in this next section.